So once again, I've done the thing again. Okay. Once again, the key things that are given to you in the problem are the variance. That's like how this machine that fills it, sometimes it fills it a little extra, sometimes it fills it a little less. And the variance kind of tells you by how much. The average, it tells you as well, is 1.08. So they have set the average a little bit higher than the 1 kilogram in an attempt to kind of make this probability small. But let's see how small do they actually make it. So that's the question. And what did everyone say? So the first thing is we're turning this statement, real life statement, that there is less than 1 kilogram in the jar into something about the standard normal, which some people call Z or Z, and that is a common letter that's used. That is the mean 0, variance 1, standard normal. That's the one on your formula sheet, or the sheet, right, is this Z, and it says the probability capital Z is less than lowercase z. That's the one we're looking at. And in this situation, what did we become? So Z is blank blank. Z is blank blank. And the first blank everyone wrote, what did they write? Haha, 45 people wrote less than. That's very good. So it's going to be Z is a less than something. Of course, by symmetry, you could flip it and turn it into greater than something else. But less than is a little bit more natural. I would go less than as well. And then here's the kicker. Less than what? Less than what? Some people wrote 1 and 2 and 6 and 10. Okay. Those are some numbers. Any other common answers? 0.3, minus 0.4, minus 2. Okay, so it looks like minus 0.4 is the most common answer. But only 15 out of 50 people got minus 0.4, and lots of other people wrote other things. Let us examine what's going on. Here's what we'll do. I'll start the solution, and then I will have you revote. So that'll be like a little hint of what's going on here. And I got to find notability, which seems to have disappeared. Notability. Okay. Okay. Okay, so with the peanut butter, and we are told mu equals 1.08 and sigma squared equals 0.04, I believe. And we want to know the probability. I'm going to call it x for the amount of peanut butter. Let x equal amount of peanut butter. And we want to know x is less than or equal to 1 or less than 1. They would both be the same. And we're going to turn this somehow into, we're going to do a bunch of steps and turn this into the probability that z is less than something. Z is less than something. And what I'm going to do is subtract the mean and divide. So the probability that x minus 1.08, let's do that, is less than 1 minus 1.08. You see, the nice thing about writing your probabilities out like this is you can do any operations you want inside the probability bracket, and I'm subtracting 1.08 from both. And then now I will divide by 0.04. 0.04. Okay. And there you go. That's a nice hint. That was my hint. And now that I've done the hint, let's revote and see what people got. Okay. Yeah, let me open it up one more time. Okay, there it is. It's open again, and you can revote. Even if you don't want to change your answer, you have to put your answer in again. And I will go back up to this hint, and let's see if people get the hint or not. Okay, very good. Okay, so it is open. I'm leaving it on this page just to let people see, and then I will take it up in a moment. let's see how you guys did with the hint and what's going on here. So I go here, okay, and we reveal the counts. Okay, less than, everybody's on less than, that's great. What is over here? Okay, let's see. Now there is a split. 9 people are in -2, but 15 people are stubbornly in -0.4. That's out of, so only about half the people have something else written. What other, one is not right. Does not exist is a good answer if you're totally confused, but only 3 people are like that. I guess everyone's all spread out to all these weird things. Oh, maybe some people put in the probability. Like maybe some of these numbers are probabilities. I don't want the probability. I want the thing that goes inside. The z is less than something, so maybe that was the mistake. But it seems to be that the 2 most common answers are -2 and -0.4. The correct answer is -0.4. So if you said -0.4, good for you. If you look at what I did, let's look at what I did. I got 1 minus 1.08 divided by 0.04. And if you do the division, that is 0.08 divided by 0.04. And that is, or negative. So that is this thing, the probability of x minus 1.08 divided by 0.04. And that is a -2. This is equal to -2. But -2 is not the right answer. So I did something wrong here, and I was trying to trick you guys, but people did not fall for it, which is great. 15 people, the most common answer was still the correct thing. Does anyone see what the problem with this this logic is? The -2 over here, this division really is -2, but the answer over here should be -0.4, not -2. Yeah. Yeah, what's wrong with 0.04? Look, there's a 0.04 right in the question. So, yeah. It's squared, yeah. This is a very important thing. Sometimes you will be given the variance, and the thing you need to divide by is not the variance, but the standard deviation. For me, personally, it helps if I have units. So I remember that the peanut butter is in kilograms. The mean is so and so many kilograms, 1.08 kilograms. If somebody gives you a sigma squared, a variance, that is in the units of kilograms squared, which is kind of an abstract thing. But to turn it into something proper, you would take the square root, and you say the standard deviation is the square root of 0.04 kilograms. And that is the thing we're working with. The square root of 0.04 is 0.2 kilograms. And what this is telling you is that on average, there's 1.08 kilograms, and you should expect it to vary by like plus minus 0.2 kilograms. That would be a very standard deviation. That would be not something unusual if it was 1.28 or if it was 0.88. Those would be kind of standard pluses and minuses. And it's very common that you mix up the sigma squared and the sigma, like I did over here. So don't do that. You should not divide by 0.08. What you should instead divide by is 0.2. And if you do it properly with the units, it makes more sense. Everything should be in kilograms. So this is some number of kilograms. This is some number of kilograms. And you're dividing by 0.2 kilograms. You should not divide by 0.04 kilograms squared. And then this really is standard normal over here. So now we're using the fact that x minus mu divided by sigma is a standard normal. So this is the standardization procedure, or normalization. Yeah, this is normalization. Let me write normalization. I'll avoid the other word. Normalization. So we have taken away the mean and taken away the variance by dividing, and now this really is z, and this calculation 1 minus 0.08 is minus 0.08 divided by 0.2. And notice that the kilograms cancel out, so it's no longer dimensional. There were kilograms on the top, kilograms on the bottom. Oh, this was really a 1 kilogram. Let me add that. 1 kilogram. And the kilograms cancel, and you get minus 0.4. You could look this up on your sheet and see what is the probability that it's less than 0.4. I guess this side is all the negatives. Oh yeah, a negative 0.4, that's what I want. Okay, negative 0.4. 0.3446, that was indeed what somebody wrote. 0.3446. So if you wrote 0.3446 in the mathematized, you had the right answer to the wrong question. The answer was negative 0.4, and if you evaluate that, it's 0.3446. That's pretty bad. If you're the peanut butter manufacturer, and 35% of your peanut butter jar is stuck, you're going to be in big trouble. So these peanut butter people are in trouble. That's the conclusion of this question. Yeah, go ahead.
Make an interjection.
Mm.
So the standard deviation here was 0.2 kilograms. And we can ask ourselves the question, is that actually a reasonable standard deviation for filling jars of peanut butter? Because they're going to be probably overfilling the jars to the point they can't even get it in the jar fairly frequently, and they're going to be underfilling a heck of a lot.
Yes.
Right? A heck of a lot.
The engineer who designed the machine probably made the same mistake we made, where they were like, 0.04, that's great, I'm done. I did the experiment, my machine is 0.04, thumbs up and walk away. And in fact, a variance of 0.04 is actually way too much variation. Right. They probably made the same mistake we did.
And they probably used,
yes.
More likely would be that the standard deviation is actually like 0.02, something like that, like much tighter.
Yes. You're saying in real life, they fix their machines when they're broken like this.
They fix their machines,
right.
and they try to get a narrow tolerance. There's another interesting thing about this, though, is that even though they're 1 kilogram jars of peanut butter, they are filling them with a mean of 1.08 kilograms, which is probably on the high side there, too. But in fact, it is usual for these manufacturers to actually, on average, fill up a little above the stated size. In other words, these are 1 kilogram jars. They typically will fill to a mean a little bit higher than that, so that the probability you get an underfilled jar is very small. And so the more they can reduce the tolerances on their machine, like get it to fill quite precisely, the closer they can bring the amount they fill down to the stated value more closely, which saves them money. But to do that, they've got to have very precise equipment that can fill the amount with a high degree of precision. In other words, they do not want to be giving you things where you go weigh your peanut butter and go, hey, I've been ripped off. I only have 0.972 kilograms. They don't like that.
The place where this comes up in real life is when you go to the airport, and you gotta minimize your probability of being late, right? And the more precisely you can arrive, then you can like, if you know you can get there within a 1 minute accuracy, you can just get there right before boarding. But the problem is, if you're going to Toronto, there's like traffic and stuff, then you got to leave all this extra time just in case. So the bigger your uncertainty is, the more extra time you have to waste, or the more peanut butter. That's why having small uncertainty is great.
It is a pain to see your plane
yes.
going off. And
well, you know what they say? They say that if you're never missing a plane, then you're arriving too early. You got to miss like 1 out of 10 planes or something.
1 out of 10 planes.
You know, that's what I think is crazy. I like to go early and sit there and do math.
I think you can do other things.
Okay, well, all right. Let's. Any questions or comments about the peanut butter problem? Yeah. Yeah. So the point is, any normal distribution can be turned into a normal random variable z by subtracting mu and dividing by sigma. Maybe the thing you don't like this squiggle. Maybe is that related to your question or not really? Yes. No, that's right. Yeah. Exactly. The whole point is you can turn any normal random variable into a standard normal random variable, and then you can use your table. That's the advantage. All right. Okay, we have a couple more things to say about the normal random variable that we'll tell you now.
Okay, let's see if, so last day we were working on this. Once we got ourselves turned around, we initially worked this one without x is less than x naught, but when we got it turned around correctly to x is greater than x naught, we worked out an x naught. You should have got 47.2. So now I want to show you a couple other ways of getting normal distribution probabilities and x naughts and things like that. And all of these things are readily programmable. There's lots of internet programs up on the internet, and we'll also take a look at R. So let's just take a look at the StatTrek one first. And here it is. So this is the what they call the normal distribution calculator, and it starts off assuming you've got a standard normal random variable that you want to work with, but it's going to give us some options here. So let's just take a look at a z-score. One of the ones we worked out before with a z-score was 2.43. So let's just put a z-score of 2.43 in there.
Wait, sorry, I missed last class. Do we know what a z-score is?
That was, yeah, we were there.
That's just
That's the z value.
so you standardize it, and it's the value.
Yeah,
okay.
it is. So
Very
this
good.
is one we started off with. And now they've given me an add, which is really irritating and probably doesn't want to go away. But I'm trying to get it to calculate. So what it will give you here is the probability z is less than or equal to z. But it also gives you lots of other possibilities here. The first one being less than or equal to 2.43, but also greater than 2.43. Of course, the equality doesn't make any difference. And then this is a very common one, is to go between plus and minus z, either what's the distance, what's the probability between plus and minus z, or what's the tail areas outside of those. So these are the so-called tail area probabilities. Other words, z is less than or equal to negative 2.43 or greater than 2.43, and we could put that together with an absolute value sign that we have done before and learn from our experts.
Hey, that's
go
us.
away, get out of here, go away, go away. So that was one, and let's just take a look at, do one more here. One of the ones we saw before was 1.96, and we'll take that. We got to take that out first because it needs to know what it's working with. And why did that go to 0? I wanted 1.96, and I wanted that out. It's a little finicky. Calculate. There we are. So these are all values that you kind of get used to, and we did work out the probability that z was between negative 1.96 and 1.96. That was our 0.95 there. And we have a couple other possibilities there. So for example, we could give a probability, a cumulative probability, such as 0.7, and it will give us what the z-score is that corresponds to a cumulative probability of 0.7. In other words, in this case, to get a probability under the curve accumulated up to 0.7 under here, that z-score is going to be negative 0.5244. And we've got some other options here too. Now that was a z-score, but we can also go for a raw score, and this allows us to adjust the mean and standard deviation. So
what does the word population mean? Why is there the word population? We've just been calling it the mean.
Well, for a theoretical distribution. That's a long discussion. Long discussion.
So we should just ignore the word population for now.
For the time being,
Okay.
We'll ignore the word population. Yeah. So we did one with a mean of 60 and standard deviation 10. And what was the one oops, there's a 10 and there's something else. Got to turn my phone off. What did we ask for? We did one where we said, well, what was the probability that x was less than 45? So let's put 45 in there.
Oh, okay, hey, well, I understand it's a lowercase x, and then there's a 45. But why on earth is this box labeled as random variable? That's truly bizarre to me. There's nothing random about 45.
No, it is the value of the random variable.
So this is just a horribly named box. This is like big thumbs down.
It is the random variable
super
is
mega
X,
fail.
and that is the value of the random variable.
Well, see, the thing is, this is also called X, but the random variable is the capital X.
Yes.
And this is the value we're comparing the random variable to.
Yes.
They got lazy. Okay.
And they didn't do a bad job in their next line.
Yes.
They did both the capital X and
but there's a good deal on it, Sephora, so that's good.
Yeah, that was a good deal.
Okay.
So before we got 0.0668 using our table. Let's see what they get for us here. And why did that just come in there? Because it wants to memorize things. Let's get that out of there. Okay, be nice to me. And why is it changed it to 25? Did I not just type a 45? Did you see me type a 45? Come on, you goofy system. Okay. Touch.
Hey, we did it.
Yeah, it did it.
Amazing.
Man, that was pretty flaky. Would you not say that was flaky?
Yeah, I'm a little skeptical of this website as a whole.
Yeah, I'm a little. So it's like, it works, but it's got weird things. And then similarly, we could have put a probability in there and got a value for the random variable. But let's go to R because it's just.
Are there any ads on R if we go to R?
Pardon?
Are there any ads on R? If we
No ads.
No ads. Okay, this is good.
No ads.
This is a good reason to learn R.
That's a good reason,
You can
isn't it?
escape the.
Okay, so let's
ads.
go to our next slide here. Oops. So 4 key functions. We used kind of 3 of these with discrete random variables like the binomial distribution. We did binomial distribution, and we bring in a 4th one in this time. So we've got P norm, Q norm, D norm, and R norm. And
Wait, what is that? That looks like it says morm.
Pardon?
Does that say morm?
Where?
Right here. It says morm.
R norm.
Oh, that's a.
There's a little space there.
Oh, okay, my mistake. I thought it said morm, and I was like, that's not the pattern. Okay.
Yeah.
Don't get mixed up.
R norm. Okay. So you'll get these slides. I'll be putting them up, and so no need to really write this down. But the idea is just like the binomial distribution. The P norm returns a cumulative probability. In other words, the probability X is less than or equal to X for some normal distribution with a given mean and standard deviation. And then we've got a bunch of others. Well, we've got Q norm returns the value of X for which the probability X is less than or equal to X equals the probability. And then we can ask, what does D norm actually do for us? And what does R norm do for us? So let's take a look at a couple of these, and I'll be pulling up R in a moment. But before I do that, I'm going to draw a normal distribution. And, well, here's one for drawing a normal distribution. And I picked this particular one for, okay. Oh, come on, don't do that to me. Why is that gone white? Why has that gone white? Tell me why that's gone white. Let's try, see if I...
Was there for a second?
Why is it doing that?
No worries, I can type it in.
Just a sec. I just want to... Cats. That is being fussy. We get some interesting electronics being the case when we have to connect things up to all the stuff here. So I'm going to type it. Are you typing it too?
I'm also typing it.
You're good. So this is,
You want me to show them what happens when you run it, the picture?
yep,
All right.
yep. And then we're going to adjust it.
Okay, here it is. Look at this. It drew some kind of curve. The curve is labeled with the word density. Why is it labeled with the word density? Please write in the word density. We could write, what could we write? Anything over here? Hello, density. And now it will say hello, density. So it'll just say whatever we want. But it does look like a nice bell curve. And it's using this d norm function. When we had d binom, I think we were kind of cagey. Why did they make d binom start with the letter d? What is d about this thing? Why on earth did they use the letter d?
And this way, it works.
But this way it makes sense. Does anyone have a guess? Why is this called the d norm? What does the d stand for? D. PG-13 guesses only, please. We're going to stand here awkwardly until someone tells me what D stands for. Yes. Derivative. That's a fantastic guess. And this is the derivative of something, but I don't think that's what D stands for. So excellent guess. Yeah. Density. It does stand for density. This is a graph of the density function, the probability density function. And remember, like the binomial doesn't have a density. It has a probability mass function. You'll remember from when I brought the pipe into class that only continuous random variables have density. But this is a graph of that density function.
So what is that density? It is the height of the curve. So it's going to draw, what we want to do is draw the curve. So we need to know the height at each of various values of x. So let's go look back at that command that we had.
There's the command.
There's the command.
What would you like to change?
Okay, so we're going to do some changes, but we're going to do some things. First of all, this curve thing here says it's going to draw this at various values of x, and this is going to say take 1,001 values of x. Okay, there's a default in there too, which is like a couple hundred, but the more we take, we get nice. Oh, that is so ugly.
If you only pick 3, it basically draws 3 points, and then it just connects the dots. But if you do 1,000, then it draws 1,000 points and connects the dots, and then it looks like a nice smooth curve. So 1,000 is a nice round number.
Nice smooth curve.
Now it looks like a nice smooth curve. That's great.
Okay, let's continue to look at this thing here. We put some limits in here. So this thing here gave the x, it gave the mean, and it gave the standard deviation. We put the mean and standard deviation in here. And then these were the limits of the x-axis. We said be 30 to 90, y 30 to 90. Well, kind of went 3 standard deviations each side of the mean. That's kind of nice. That gets almost all the probability. So I went 3 standard deviations of the mean, and then I did y-lim values from 0 to 0.4. And when we drew our graph, let's look at that graph again. I looked at this and went, yeah, that's not very nicely drawn because this is pretty low. I could have made better use of my space if let's go to 0.1.
Let's go to 0.1.
Let's go to 0.1.
So I replaced the y-lim instead of being 0 to 0.4. Let's make it 0 to 0.1. What does C stand for? Why do we need a little C? What does that stand for? Is that column? Or we don't know. It's magic.
It's concatenate is one of the
concatenate.
things. Concatenate, but it's used whenever we need to
Have a little range.
A little range, yeah.
Okay, very nice.
Okay.
Well, there we go. 0 to 0.1. We could even we could shrink it a little more. Let's go 0
that's
to.
pretty good.
Let's go to 0.06.
That looks
nice. Whoa, yeah. Now we're cooking.
Okay. That's
Beautiful.
looking pretty nice. Now, okay. So there was a line width thing that changes the thickness of the line. That's not really a big thing. You know what? I don't like the color of your curve.
What do you mean?
It's just like
How rude.
How
do I change the color?
I'm
I'm gonna try color equals, and then I'll try
COL equals.
COL. Okay.
COL equals.
Equals.
What color would you like it?
I don't know. Let's see. If I put blue in quotes, does it know what I'm talking about?
Okay, you can do blue.
Ooh. Yeah, that's better. That is better.
That is bad.
That's a nice improvement.
Isn't that nice?
Okay.
Isn't that nice?
Fantastic.
So we have used this to draw some curves. You can play around with this, and what happens if we change the standard deviation on this curve? Let's just actually cut the standard deviation on this one from 10 to 5.
Okay, so
Leave it exactly like
I'm just
that.
changing the second parameter in the D norm from 10 to 5.
10 to 5.
Whoa! Hey,
Oh,
it's too tall now. Oh, oops.
We cut its head off.
Oopsie doopsie. Don't worry, we can put the head back. Plus, I increased the Y limb. All right, there we go.
There it is.
Lovely.
Okay, so
Lovely.
you guys sometimes make like adjustments to get things looking nice. And, well, there's various other things you can do. You can overlay normal curves and that kind of thing. But that's not so critical for us right now. Okay, okay, that's all we want to say for now.
Okay.
And
yeah, any questions or comments about this? So this is useful for calculating things you're going to have a homework assignment where it'll say like, the peanut butter jar has this much and this much, calculate something. And one of the ways you can do it is to use R to draw these little graphs or to calculate different probabilities. If instead of doing D norm, you did the P norm, those are the probabilities, then it's this nice smooth curve that goes from 0 to 1. So you notice the values here on the axis are no good. So if you could look up the probabilities, what is the probability it's less than 60? That should be exactly 0.5. So you can get all sorts of things. You can type in to get the values. Let's get the P norm. What's the probability? It is less than, let's do 70. That's 1 standard deviation above the mean. That's the P norm function. And when you run it, you get 0.841. This would be on your sheet as well, but just another way to do it with the computer. Okay, questions or comments about any of this calculating stuff? All right, we're going to move on to something completely different now. So one of the last topics of the course. A great question you might have is, why are we so obsessed with the normal? Why do we care? This is a great question to ask yourself. For many situations in life, why do we care? Why are we torturing with the normal? Why do we have a page with the normal distribution? So the subcategory, why is the normal special? The normal. It's so special, we gave it the name normal. Why is the normal special? And I think we have done nothing to answer this question so far. Does anyone want to take a guess to answer this question? We're going to spend several classes getting to the answer to this question. We're going to do it the slow math way, where we're going to build up some tools that explain the answer to this question. But maybe let's spend a minute. Let's have just off the top of our heads. Why is the normal special? Why do we like it? Yeah. Yeah, but why the normal and why not some other shape? Like why this special one? So I like your answer. You're like, this is great. We just did a question and we had this as the probabilities, and you're exactly right. It does represent probabilities. But why this and not, there's one in my area of research. I study random matrices, which is some complicated things. Random matrices. And in the random matrix world, there's another distribution called the semicircle law. Can you guys guess what the semicircle law looks like? It looks like this. Okay, this is the so-called semicircle law. This is some advanced stuff. The semicircle law. How come we teach you the normal distribution, but we don't teach you the semicircle law? The semicircle law we save for graduate school. The normal distribution we teach in first year. Why is this one more special than this one? Yeah. Yes, it does go to infinity. This is true. This makes this one more annoying. This one's harder to deal with. This one, it has these points where it sort of ends. And so this one's actually harder in some sense than this one. So this one goes to infinity. The way we say this sometimes is this has unbounded support. Unbounded support. This one has bounded support. The support is where the probability is greater than, the density is greater than 0. So this has a bounded support. And this one has unbounded support. So that makes this one harder. Yeah. Yeah, this is a weird fact. Why is the normal special? The answer is everything in nature, or many things, let's say many things in nature. So we cover ourselves. Many things in nature seem to follow it. And I think we mentioned this very briefly. at the beginning seem to follow it. Follow it. So if you remember when we introduced the normal, we said if you take a bunch of Scottish soldiers and you measure their chest circumference, so you get a little ruler out and you give Angus a big hug and measure his chest circumference, the distribution of their chest circumferences seem to follow this normal. And it's not just that, but many things in nature. Almost everything seems to. Great, we answered the question. If you are sort of happy with this, then you stop there. But of course, we're not happy with this because we're mathematicians. So we have a follow-up question. Why do many things in nature follow this? Why do many things in nature? Many things in nature follow this. And this is a fantabulous $1 million question. And we're going to work towards answering it. And I think last year when we taught the course, we got to a nice answer of this right at the end of the course. So we're going to move in that direction and try to explain this slowly. And that's what we're doing for the next little bit. So it might seem a little abstract, but we really are trying to answer this big question. Why do many things in nature follow this normal distribution? What is special about the normal distribution? And the very kind of like, here, the summary answer is if you have your normal distribution. I'm going to draw my normal distribution in a bubble so I can think of it as an idea. Here's the normal distribution, the bell curve. Ooh, that's not, I didn't do a great job drawing that, but that's okay. Okay, this is the bell curve, the normal bell curve, bell curve. Let's draw for completeness. Let's also draw the semicircle law over here. This is the semicircle law, which is a different distribution, just so I can contrast them. Many things in nature, it turns out there is a reason that many things in nature, as the systems get larger and larger, they get closer and closer to the bell curve. So there is some system in nature, I'm going to say a system in nature with some number of parts. Let's say one part, and that'll be over here. And then there'll be another system in nature with 10 parts, system with 10 parts. And there'll be a system with 100 parts. And the more parts you add to it, the closer and closer it gets to the normal distribution. And this happens on all sorts of things. So as you add more and more things, kind of all of the distributions in nature, they tend to be very, very close to the normal distribution. As they have more and more individual little parts, they get closer and closer to the normal. We are going to explain this. There's a famous theorem that does this called the central limit theorem that says essentially this, central limit theorem. And we're gonna do it in more detail soon. But it says, very roughly, the more parts, the closer you get to the normal. Okay, and this is, for example, this is the very colloquial way of thinking about it. For example, the Scottish soldiers, the chest circumference of a Scottish soldier depends on a lot of different factors. It depends on how much meat they had when they were a child. It depends on how much they exercised. It depends on their genes. All of these things combine to give one number, which is their chest circumference. And so it really is a system with thousands and thousands of inputs into that help determine this Scottish soldier's chest size. And that is why it's very close to the normal distribution. Other things in nature, sometimes, occasionally, don't follow this. And a good example is random matrices. They go this way instead. So I'll say random matrices. Or maybe more specifically, the eigenvalues of random matrices. If you know what an eigenvalue is, then you will be excited by this. So not literally everything goes towards the normal distribution, just certain systems that are made in a certain way, as long as they have lots of parts, they go to the normal. And that tends to happen a lot in real life. And this is the process we want to understand. So we want to understand how this works. How to understand this. And to understand this, we're going to have to talk about these kinds of approximations. What does it mean for something to get something closer to something else? So we must understand. Approximations of random variables. Approximations of random variables. So this idea that we want to get to of something getting closer to something else, this is the idea of an approximation. Another way of thinking about it is limits of random variable. Both of these kind of mean the same thing. Other distributions that are not the normal distribution will get closer and closer to the normal distribution in a certain sense. So that's what we're going to work on for the next little bit. understanding these approximation or limits as things get bigger and bigger. And our first example is going to be a dice with many sides, a dice. Example 1. This is the first example of many, a dice with many sides. Many sides. And so we're going to look at a dice with a lot of sides, and we're going to ask, is there a nice way to approximate a dice with a lot of sides as the number of sides gets bigger and bigger? So can we approximate it? We approximate it by something else. By something else. By something simpler as the number of sides increases. And that's the idea. So the big idea is we want to understand, why do we care about the normal distribution? The answer is the normal distribution comes up as sort of the limit point, the attractor. Things tend to get close to it in a certain sense. And how we're going to understand this is approximations and limits of random variables. And we're going to start with a dice with n sides. Many sides. Let's make it precise. With n sides. So a dice with n sides, where n is some number. You're probably used to n equals 6. If you're quite fancy, you might also have a 20-sided dice at home, n equals 20. And we're going to see what happens as n gets bigger and bigger. That's where we're going. Any questions or comments so far about any of the stuff that I've said, to give you the big picture first before we jump into the details? Okay, let me open up a mathematized question here. We're going to move into this many-sided dice situation. And where's my mathematize? I think it is in a different window. Mathematize. Here it is. Okay. How many sides are on my dice? What can we say about a dice roll when the number of sides gets larger and larger? To help us, Professor Nika has brought in some large number of sides dice. What is the maximum number of sides on a real-life dice he has? So in my backpack, I have some unusual dice, and I want you to guess what you think the number of sides my dice have. Okay, I'll let you think for a minute. Take your guess. Of course, this is mostly for fun, but we will end with this. Okay, time's up. Let's see. What do you guys think? What kind of dice do I have? All right. Some people are at 60, a little spread out. Let me show you some of these wild and wacky dice that I have brought in. To start with is sort of everybody's favorite. Oh, so this is a good one. This is a really wacky one. It's a 10-sided dice, but it's got numbers that end in 10. So this is kind of a weird dice. The numbers I'm going to use are all actual numbers. And so the starting one I got is this 20-sided dice. This is everyone's favorite from D&D. The nice icosahedron, beautiful little dice there. This is kind of a classic, but we can go past that. This one, I think, is a 24-sided dice. Or is this only so this might be a 16-sided dice. Okay, we want to go past 20. This one, I think, is a 30-sided dice. It's starting to look a little bit like a golf ball here. You can see the faces are these little rhombuses, these little quadrilaterals. Go even more. Oh, look at that! Amazing. Okay, but we can actually go even further than that to this bad boy. Ah, the outrageous 60-sided dice. It basically looks like a golf ball. If I roll it, you will see it rolls forever. Let me roll the dice here. So if you pick 60, then you are wrong because I also have a 100-sided dice. This is the 100-sided dice that truly is a sphere. So this one, you really have to not touch it for a while. And look, I've rolled a 26. Amazing. Let's do it one more time here. You really got to like too long. Okay, there. I rolled a 4. I'm not very lucky today.
Now you can tell which is the up top face with certainty.
I think you can. Yes. Yeah. So it has little divots, and I think it is a 4 there. You need to have an exceptionally flat surface, but this is how it goes. So what is the moral of the story? The moral of the story is the 100-sided dice is quite unruly, and we're going to do some nice math to figure out, instead of using the 100-sided dice, could we do it using the random number button on your calculator? Your calculator probably has a little random number button, and instead of using this 100-sided dice, we're going to show you how you can approximate this 100-sided dice extremely accurately using something much simpler. And we're going to do that all on Friday's class. So we'll stop here. If you have any questions or comments, please feel free to come up. If you want to come see the 100-sided dice, please feel free to come and investigate. And we'll see everyone on Friday. AliExpress. Yeah.
Can you actually see flat sides on that? This
Yeah,
is
very barely. Well, I mean, it stops rolling. So
boy, they're
yeah.
you can just barely feel them. They're not sharp.